All right, let us get started. So, hello and welcome
Sir,
everyone to the eighth week
uh,
of interactive live sessions for the course on fluid dynamics and turbomachines. This
sir,
course is being
एक
offered
मिनट
by NPTEL and is being instructed by Professor Shamit Bakshi and Professor Dhiman Chatterjee from the Department of Mechanical Engineering at IIT Madras. My name is Debjit. I'm a PhD scholar at IIT Madras and I'm the TA for this course. And like every other week, we shall be solving some problems together and having discussions regarding anything related to the course. So if you have any questions, you can ask right away. No need to hesitate.
सर मेरा जो असाइनमेंट है अपना
Yeah.
सेवंथ असाइनमेंट जो लास्ट क्वेश्चन है नंबर 13 एंड 14
Okay.
वो जो आंसर आया है जो डिस्चार्ज का 0.089 और 25.49 टर्बाइन रनर जो है स्पीड स्पीड लिखा है 13
Hmm.
एंड 14 का आंसर करेक्ट है मेरा वो रॉन्ग दिया है सर ने
Is it so? Okay.
13 and
So
14
uh, let me note that down. So these things are actually uh, handled by the NPTEL team. So if you have any discrepancy, you can send over an email to them.
ओके ओके
Let me check. So it's last two questions of week 7 assignment,
सेवन
correct?
सेवन असाइनमेंट
Okay. Okay, I'll look into it. Thanks. All right, so let us get started. So this is the first question of today's session, which is asking us what is the speed of sound when a sound wave is flowing through an ideal gas. So is it option A, square root of RT, option B, square root of gamma RT, is it option C, square root of P over rho, or is it option D, square root of gamma P divided by rho? And these symbols carry their usual meaning. R is the gas constant, T is the absolute temperature, P is the pressure, and rho is the density. And gamma is the ratio of the two specific heats, one under uh, constant pressure to constant volume.
पी बाय रो
P by rho. So I assume you mean option number C, correct? Okay, so here's the first question of today's session, which is asking us what is the speed of sound in an ideal gas? Is it option A, square root of RT, option B, square root of gamma RT, option C, square root of P over rho, or option D, square root of gamma into P over rho? Let's take a look at the solution. It's actually option B, square root of gamma RT. So the speed of sound through an ideal gas is given by square root of gamma RT. So if you plug in the usual values, then this is somewhere around 330 meters per second. This is for flow of or the speed of sound in air at uh, ambient temperature. Okay, let's move along. Move on to question number 2, which is asking us that
Sir,
for an
speed of
isentropic,
sound in air and speed of sound is water. Which is more?
uh, so it's higher through water because it really depends on the compressibility of the medium through which it flows. If the compressibility is less, then the speed would be higher. So for a perfectly rigid body which has no compressibility at all, ideally the speed of sound would be infinity. So for the usual materials, the speed of sound in metals are the highest, solid metals, and in liquids it's a bit lower, and in gases it's the lowest.
In water, 540 meter per second. Na?
Yeah, so
Oh,
somewhat like that.
okay, okay.
Yeah. And for a perfectly compressible material, that speed would be zero. Sound won't travel at all. So those are the perfectly rigid and perfectly compressible. Those are the two unrealistic but extreme cases. Everything that falls in between is something that we discussed here. Okay, so coming to question number 2 of today's session, it's asking us that for an isentropic flow within an ideal gas, when the Mach number at the throat of the converging diverging nozzle, also known as a CD nozzle, is unity, the flow is said to be what? Is it option A, subsonic? Is it option B, sonic? Is it option C, supersonic? Or is it option D, none of the above? So, a few things to unpack here. So, a converging diverging nozzle is something like this. It converges initially and then it diverges. The area wherever it's minimum, this is called the throat. This is a CD nozzle. Flow usually happens in this direction from left to right. And so another thing is that this is an isentropic flow where there is no increase in entropy. And if the Mach number at this throat is unity, meaning equal to 1, what kind of a flow is that? Is it option A subsonic? Is it option B sonic? Is it option C supersonic? Or is it option D none of the above?
Sonic.
Sonic. So that's option B. Alright. Let's take a look at the solution. Sorry, it should be sonic. So forget the colors. This is not the right answer. Sonic would be the correct answer. So coming back here, sonic is the correct answer. So before this, in the converging part of the nozzle, it would be subsonic. Here it becomes sonic if Mach number is 1, and the flow over here in this region, it would depend on the back pressure here. So if it is uh, so there are two possibilities. It could again, so if PB is higher than the critical value, then it would again decelerate after the throat and become sonic. And if the back pressure PB is even lower than that, even lower than the critical value, then the flow over here would turn supersonic. So in supersonic flows for diverging sections, when the area increases, the velocity keeps on increasing and the pressure keeps on dropping, which is why the correct answer here would be B, sonic. This is only at the throat, by the way. This uh, minimum area cross section in this converging diverging nozzle. Hope that's clear. Any questions on this?
No.
Okay. So let's keep moving. We'll move on to question number C now. Question number 3 now. So this is asking us what is the ratio of stagnation temperature to static temperature for isentropic flow of a perfect gas or an ideal gas? Is it option A, 1 plus gamma minus 1 by 2 m squared? So here m is also the Mach number, ma, which is the usual notation that we have used, but here it's m, and gamma is the ratio of the uh, specific heats. So the question is, what is the ratio of the stagnation temperature to the static temperature, meaning T0 over T? What is it equal? Is it option A, 1 plus gamma minus 1 by 2 Mach number squared? Is it option B, 1 minus gamma minus 1 by 2 m squared? Or is it option C, 1 plus gamma plus 1 by 2 m squared? Or is it option D, 1 minus gamma plus 1 by 2 m squared?
A value.
Sorry?
A.
A.
1 plus gamma minus 1 upon 2 m square. A.
Okay. So let's take a look at the solution. It's correct. Perfect. Good. So let's keep moving. We'll move on to question number 4 now, which is asking us that for compressible flow through a nozzle, choking occurs when? Is it when option A, the exit velocity equals Mach 1? Or is it option B, the throat velocity equals Mach 1? So if this is my nozzle, this is the exit velocity VE, and this is, let's call it throat velocity VT. So when does choking occur? Is it when Vt corresponds to Mach 1, meaning Cs into Ma, where Ma is 1, so it should be Cs? Or is it when the exit velocity is equal to Cs into Ma, once again Ma being 1?
Velocity equals match 1. Mach number 1.
Exit velocity or throat velocity? Which one?
Root velocity equals Mach number 1.
Throat velocity equals. It's option B. So this is question number 4 of today's session, in which we're asking that in a compressible flow through a nozzle, choking occurs when? Is it when option A, the exit velocity equals Mach 1, or is it option B, the throat velocity equals Mach 1? So we have received one response in favor of option B. Let's hear what others have to say. You can either type in the chat box or you can unmute and answer, whichever way you feel comfortable. Here we have another response in favor of, sorry. So we've got two more responses in favor of option B. Let's take a look at the solution. And it is option B, correct. So if we go back here. So this is when the flow chokes, and we can keep decreasing the back pressure after this. That would not increase the mass flow rate through this uh, converging diverging nozzle. So the maximum mass flow rate that we can obtain is at when the throat velocity becomes corresponds to a velocity which is Mach number 1. After that, we can uh, keep decreasing the pressure. The exit velocity would keep on increasing, but it would increase at the cost of a lower density. The mass flow rate itself won't decrease further. Any questions on this? Okay. So if not, we will keep rolling. We'll move on to question number 5 now, which is asking us that in a steam turbine, the nozzle uh, performs a energy conversion. What sort of an energy conversion is that? Is it option A, from heat energy to pressure energy? Option B, from pressure energy to kinetic energy? Or is it option C, from kinetic energy to pressure energy? Or is it option D, from mechanical energy into thermal energy?
Option B.
Okay, so
Option B.
we have one response in favor of A and two responses in favor of option B. Let's take a look at the solution. It is option B. Correct. So where does this sort of a conversion take place from heat energy to pressure energy? In a uh, not just a steam turbine. So in this case, you have to consider the whole steam power plant. So in that entire cycle, where is it that heat energy is converted into pressure energy? Any guesses? It's actually in the boiler where this happens. So the heat energy released by burning fuel is transferred into the uh, supercooled or subcooled liquid, which then undergoes an increase in its enthalpy. So first of all, the liquid uh, vaporizes and evaporates and transforms into steam, and also adding further heat to it increases its temperature as well as pressure. But in the nozzle, which is just before uh, the actual steam turbine blades, over there, this increased pressure is converted into kinetic energy. You so there's this terminology that a nozzle expands a fluid. So basically its density decreases, the pressure uh, decreases, and it's converted into kinetic energy. D-level nozzle could be one. It could be a subsonic nozzle as well. Only a converging nozzle. Even in that, the pressure is converted into kinetic energy more. So the pressure decreases and velocity of the fluid increases. and then that high velocity fluid then goes on and hits the runner blades and makes it rotate, which is then which rotation is then used to uh, generate electrical power using an alternator. In the question it should be mentioned. So this is true for all kinds of nozzles, not just the Laval nozzle or any other kind of a nozzle. Okay. Any questions on this?
Opposite of nozzle is diffuser.
Correct.
In the case of function, nozzle increases velocity, diffuser increases pressure.
Correct. Correct. Okay. So if there are no more questions, we'll keep moving.
Sir, mechanical energy is into thermal energy. Which device?
It's basically friction, right? So if you rub your hands, your mechanical energy gets converted to thermal energy.
And C1 alternative kinetic energy into pressure energy. It means centrifugal pump.
Your diffuser is one example where velocity decreases but pressure increases in that case, right?
Centrifugal pump also one of the example.
Correct. Yeah. So there you supply energy and increase the pressure. Okay, let's keep moving. We'll move on to question number 6 now. So this question is that a gas turbine is classified as a closed cycle when what happens? Is it option A, when air is compressed, heated and expanded continuously and then exhausted? Is it option B, the working fluid is recirculated within the system? Is it option C, when there is no combustion chamber? Is it option D, the turbine is only when the turbine is used for aircraft propulsion? Okay, we
The
have
working fluid is recirculated within the system. B alternative.
okay. So we've got two very quick responses in favor of option B, when the working fluid is recirculated within the system. Let's hear what others have to say. So a gas turbine is said to be operating on a closed cycle under what conditions? Is it when option A, air is compressed, heated, and expanded continuously and then exhausted? Is it option B, when the working fluid is recirculated within the system? Is it option C, when there is no combustion chamber? Or is it option D, when the turbine is used for aircraft propulsion? Okay, we've got another response in favor of option B. Let's take a look at the solution. It is option B, correct, when the working fluid is recirculated within the system. So this would mean something like this. So um, I have to use two heat exchangers. There will be one turbine where it is expanded. So this is a heat exchanger where heat is added to the system. This is where it is released. This should be a compressor of some kind. This is a turbine where the expansion happens. So you see, this is a closed loop where the working fluid is keeps circulating within the system, and it only exchanges uh, heat and work. It does not, no new mass is introduced into the system, or the current mass is not allowed to exit the system. Whereas compared to the actual, in so one major application of gas turbines are in aircraft propulsion systems, where uh, you know this part is missing. Sorry, uh, this part is missing. There is no heat exchanger which cools down the exhaust fluid and then uh, it keeps it recirculating. Instead, uh, it starts off with a compressor which takes in air, and then it goes through a combustion chamber. So I should really rename these things. C is compressor, CC is combustion chamber, and then after combustion, so there is a fuel in as well. So fuel is usually sprayed within the compressed air, and then after combustion, that very hot and high pressure gas then flows into a turbine and rotates the turbine blades, and then in the end it is exhausted out. So you see, every time fresh air comes in, and whatever after combustion and expansion, the exhaust gases, they are released out of the system. So it's not really, so the working fluid keeps changing, it's not recirculated anywhere. So this is a open cycle, whereas this one is a closed cycle. Any questions on this? Closed circuit application. So, steam turbines are a case where it usually operates on a closed cycle. Other than power plant, okay, there could be gas turbines which use the same working fluid as well, but not in aircraft propulsion, but more land-based operations where gas turbines are used to generate power, electrical power for household or other applications.
Vapor compression system is a closed cycle.
Which one? Sorry.
Vapor compression system in refrigeration system is a closed cycle.
Yeah, those are closed cycles as well. So there also the refrigerant isn't allowed to leak, but it's the same fluid which keeps on recirculating. All right, let's keep moving. Move on to question number 7 now. This is asking us, what is the main purpose of using compounding in a steam turbine? Is it to option A, increase the overall efficiency? Is it option B, to reduce shaft speed to practical values? Is it option C, to reduce heat loss? Or is it option D, to increase the exit velocity? Okay, we have one quick response in favor of option B, to reduce the shaft speed to practical values. Sorry, let's hear what others have to say. Okay, another response. Uh, Sorry, in favor of option B.
A option.
Option A, to increase the overall efficiency. Let's take a look at the solution. It's actually option B, to reduce the shaft speed to practical values. So what compounding does is that instead of one stage, we use multiple stages of uh, the turbine blades, as well as stages would include one, either a nozzle or guide vanes, and one set of rotor blades. So those two together is called one stage, and if you use multiple such stages, that's called compounding. Now, what happens is that in case of impulse steam turbines, the if you reduce the entire pressure down to the ambient pressure at once, then the velocities are of the order, higher than 1,000 meters per second, something like uh, 110 meters per second. So this is the gas velocity. Let's not call it V, let's call it C, in accordance with our uh, notations. Now, in this case, if you want to maximize or optimize the energy transfer from the uh, high speed steam to useful energy generated by the blades, then the blade velocity would have to be half of that velocity. So something like 550 meters per second. And uh, So this is the blade velocity. Now for usual blade sizes, this would correspond to an RPM, a very high RPM, something like 30,000 to 50,000 uh, rotations per minute, or revolutions per minute. Now, this is not really useful because we have to then use a gearbox or some other mechanism to rotate another shaft at a much lower, much more practical RPM, which corresponds to the frequency of electricity which we want to produce, which is like in India, it's 50 hertz, right? So this is why, to reduce the shaft speed or shaft rotation velocity, we have to use compounding, in which multiple stages are used. So, as we learned, there are various kinds of compounding, but the main purpose of doing that is to reduce the shaft speed to more practical values, so that I don't have to use additional mechanisms like a gearbox or any other velocity reduction uh, mechanisms, so that I can get the desired frequency which I want. And also another purpose is to reduce the exit velocity, which is wasted when uh, the the working fluid leaves the last stage of the turbine, or in case when we are not using compounding, only one rotor is there. So when it exits the rotor, it should exit with as low a velocity or as low a kinetic energy as possible, which means that we have extracted as much of that energy as possible. It's through size of rotor. What do you mean by that? I'm sorry, I can't understand. Diameter. So diameters could really be pretty huge in cases of uh, practical steam turbines, because they handle a lot of mass flow rate. So the diameters have to accommodate that. So for this kind of a RPM, so let's consider this. So in this case, what you'll see is something like this. So pi d being the circumferential uh, distance multiplied by u being, wait a second, if u by pi over d is something like 550, 550, 3000, 30,000. 30,000 rotations. Now this is per minute. So and if this is in, if U is in meters and D is in, U is in meters per second and D is in meters, then you have to convert this to rotations per second. So this would be 60, and U is something like 550. So you now do the math. So your D typically would be, sorry,
60 multiplied or divided?
multiply or divide. I think it should be divide. So this is, so
Divided.
u is the velocity, which is in meters per second. Then this is in meters. So this should really give me how many uh, uh, circumferential distances am I traversing over a second. U equal to pi dn by 60. Yeah, so that is, so this is exactly that, right? So u equal to, if pi dn, then n should be u by pi d, which is what I'm using here. So d would be u over pi into this much. Let me use a calculator. Pi into 30,000 into 60. Yeah, so this is giving me a very low value, which is not really practical.
60 should be divided by, sir, not multiplied. Divided by 30,000. 30,000 divided by 60, not multiplied by 60. To convert RPS, RPM to RPS.
Okay,
Wrong, 60
yeah.
wrong in a multiplied by. Correct, correct.
So this should give me something like 500, right? Yeah, correct. So this is like 1 over 3. So yeah, that's more practical. So this is like zero point 0.3 meters or so. 350 mm at 3000 RPM. Yes, that makes sense. Yeah. So around that. So this is zero point 0.3 meters is a more practical diameter of a rotor. Does that make sense? Yeah, and thanks for helping me with that. I was making a silly mistake with that RPM to RPS conversion. Were there some other messages over here? Check. Not missing any. Steam jet velocity 1000. Yeah, yeah, something like that. Of that order, basically. Okay. Any other questions regarding this? If not, let's keep moving. Okay. It's coming to question number 8 of today's session. It's being asked to match the following. We have two options each on two columns. On the first column, we have two types of turbines, a Rato turbine and a Curtis turbine. And the two options in the second column is option 1, velocity compounding, or option 2, pressure compounding. Now, what form of a turbine uses what type of compounding? You have to match them with each other. So there are really two combinations possible. Either it's A1B2 or A2B1.
In Curtis turbine, velocity compounding is used, and Rato turbine, pressure compounding is used.
So that's option B, correct?
B.
Yeah. Okay. So let's hear what others have to say. This is question number 8 of today's session, which is asking us to match the following. We have option A, Rato turbine, and B, Curtis turbine on the left-hand column, whereas on the right-hand column, we have uh, 1, velocity compounding, and 2, pressure compounding. You have to match the type of turbine with the form of compounding. And there are two options given below. It's either A1, B2 or option B, A2, B1. So far we have received one response in favor of option B. Let's see what others have to say. Okay, let's take a look at the solution then. It's actually option B, A2, B1. So in a Rato turbine, a pressure compounding is used where after each stage, the the guide vanes uh, reduce the pressure and increase the velocity of the flowing steam, whereas in a Curtis turbine, a velocity compounding is used, where the entire pressure drop and velocity rise happens in one nozzle before the first stage. After that, after that, pressure uh, does not decrease anymore. It's only the velocity that reduces after each and every stage uh, of the rotor blades. And there are guide vanes in between, which uh, merely deflects the steam and doesn't really do anything to its pressure or velocity explicitly. Any questions on this? If not, let's keep rolling. We'll move on to question number 9 now, which is asking us that for a gas turbine operating in the Brayton cycle, the cycle efficiency increases with what? Is it option A lower compressor pressure ratio? Is it option B, a higher turbine exhaust pressure? Is it option C, a higher compressor pressure ratio? Or is it option D, a lower turbine inlet temperature? So let me draw the usual Brayton cycle again. So air comes in through a compressor C, then fuel is added and it is set on fire. So that's the combustion chamber. And after that, it goes through an expansion process in a turbine and it is finally exhausted out. This is the typical Brayton cycle.
Higher compression ratio.
Higher
C option.
compression ratio. Yes. So C.
Because the formula for efficiency is 1 minus 1 upon RP raised to gamma minus 1. As pressure ratio increases, velocity also, efficiency also increases.
1 minus RP, gamma minus 1 by gamma, right?
Gamma minus 1 by gamma.
Yeah. Okay. So we have received one response in favor of option C. Let's see what others have to say.
Sir, same formula is used for auto cycle efficiency. In auto cycle efficiency, the formula is 1 minus 1 upon RC raised to gamma minus upon gamma.
Yeah.
Air pressure ratio, their compression ratio
Yeah.
in auto cycle efficiency.
Correct.
Okay, okay, thank you.
The only difference is that, an auto cycle which is used in IC engines, over there, it's not a rotary type engine. Over there, it's like the whole process is intermittent. Whereas a Brayton cycle, which is usually used in gas turbines, those are turbo machines, so to say, and those are constant rotation machines. So the operation is much smoother in those engines. Okay, let's take a look at the solution. It is option C, correct? So, and the formula for efficiency is also correct. So RP is the pressure ratio through the compressor. So RP is basically, so if we call this 1 and we call this 2, then RP is basically P2 by P1. The pressure, so the ratio of the two pressures, and that's caused by the pressure rise due to the compressor. So higher we can make it, the cycle efficiency increases, but there are practical constraints to how high we can do that. Right? Okay. So let's keep moving. So this is the last question of today's session, which is asking us what is the relation or how is the nozzle efficiency eta n related to the nozzle loss coefficient zeta n, and there are four expressions given below. You have to pick out the correct expression. Is it option A, eta n equal to 1 minus zeta n? Or is it option B, eta n equal to 1 by 1 plus zeta n? Or is it option C, zeta n equal to 1 minus eta n square? Or is it option D, eta n equal to square root of 1 minus zeta n? This is question number 10 after a session, which is asking us that the nozzle efficiency eta n is related to the nozzle loss coefficient zeta n by which of the following expressions? Is it option A, eta n equal to 1 minus zeta n, or option B, eta n equal to 1 by 1 plus zeta n, option C, zeta n equal to 1 minus eta n squared, or is it option D, eta n equal to square root of 1 minus zeta n? So the nozzle loss coefficient is the ratio of losses in a given turbine, mainly due to frictional losses, divided by the total uh, energy or enthalpy that goes into the nozzle, whereas the nozzle efficiency is given by the uh, actual uh, isentropic expansion performed by the nozzle to actual change in enthalpy caused by the nozzle to the isentropic uh, enthalpy change that could have happened if there was no losses, if the entire process was perfectly isentropic. Okay, let's take a look at the solution. It's actually option B. So, you know, there are three things which are related to the nozzle performance. That is this nozzle efficiency, nozzle loss coefficient zeta, and there's another thing called Kn, which is the nozzle velocity ratio. So that's the ratio between the inlet and the outlet velocity. So one relationship we know is that uh, the uh, velocity coefficient square is equal to efficiency, and the way it is related to the nozzle loss coefficient is in this way. So imagine this. This is the zeta n is the loss, right? So the if so the entire thing would have been what we could convert plus the losses. So if the losses become 0, then the efficiency would become 1. Okay, so that was the last question from my side. Thank you. If you have any questions, you can ask. Otherwise, we will close the session.
In next Sunday, there is exam, sir. Film Dynamics and Turbomachines. How
Sorry,
many questions weightage for numerical?
I'm not really sure. I can't really help you with that.
Okay, okay.
Anything else related to the content of the course?
Content is good, sir. Very interesting subject.
Okay, thank you. So, the sessions end today, and it's been a great learning experience for me throughout. I don't know whether it has been the same for you, but I had fun doing this. Thank you.
Sir, you are a research scholar,
Yes, sir.
PMRF.
Yeah,
Which specialization? Thermal engineering.
not really. I'm in the applied mechanics and biomedical department.
You are from which city?
I myself am from Kolkata.
Okay, okay, okay. Thank you, sir. You are from
Thank you.
IIT Guwahati?
No, IIT Madras.
IIT Madras. Okay. Thank you, sir.
Thank you.
Sir.
Yeah.
Thank you, sir. In the last question, 10th number, KN, last 10 number question.
Hmm.
The KN is efficiency square. What is that?
Oh,
Parameter called as.
right. These two, right? So Kn is basically the velocity ratio, whereas, uh, so C2 by C1, and efficiency is C2 squared by C1 squared. So if you replace this, you can find out the relationship between these
Okay, sir. Thank you, sir. The course content is very in depth given. It's very big syllabus.
two. Yeah,
But
true.
the teacher are very, it's very good that in depth they have given their heart to teach that subject. We are
Right.
very grateful to you all, IIT Madras team, and
Right,
we
yeah.
are
Both,
to you also.
Professor Bakshi and Professor Charit, they are very well-known people, and they are well-known for the right reasons. They are,
Yes, sir.
giants in this field.
Yes.
Yeah.
If any, suppose I have some question about uh, reaction turbine, then I can write a email to them, right?
Yeah, you can.
Okay. Thank you, sir.
Okay, thank you.
Thank you.
So that brings us to the end. Thank you all, and all the best for your exams.
Thank you, sir.
Thank you, sir.